Okay, welcome to the second lecture this week. So we've been looking at the evolution of stars last time. So how the endpoints of different stars depend on the initial mass. So I left you with this little problem to look at the average density of a white dwarf stars. This is basically what the sun will end up like. So in previous problems, you've calculated the average density of the sun and got a number, around about 1,000 kilograms per meter cubed, so similar to water. But here we want to explore this white dwarf star, which I told you had a mass just over half a solar mass, so 0.6 of a solar mass. And I told you it was about the size of the Earth. So again, you could go away and look up the radius of the Earth. So obviously density, average density, just total mass over total volume. So 4 times pi r cubed for the volume. So 6,000 kilometers is close enough. It's probably 6,500 if you want to be a bit more accurate for the radius of the Earth, or 1% the radius of the sun, which would be about 7,000 kilometers. It's a typical size for a white dwarf. So if you work out those numbers, you come up with 10 to the 9 kilograms per meter cubed. So that's 10 to the million times more dense than the sun is now. So once all the nuclear fusion and everything is stopped and the core of the star contracts down after the planetary nebula stage, then it leaves behind this very peculiar object called a white dwarf star. In future modules, you'll learn that it's basically literally held up by quantum mechanics and the Pauli exclusion principle, which is kind of interesting. And again, another way of capturing that is that the material that in a white dwarf is 100,000 times more dense than lead. So this is extremely weird material. Okay. Not quite as weird as the neutron stars, but already pretty weird. Okay, so today we're going to continue that sort of theme of looking at ways of studying the evolution of stars. And this is going to lead us today to look at star clusters. So these are clusters of stars, so not stars by themselves, clusters of stars. It's actually my nice background that we have here is a picture of a star cluster, a very nice one. And so those are what we're looking at today. So let's define what we mean by a star cluster for starters. So basically, it is what it says. So it's a collection of stars that is concentrated in space. So rather than sort of stars being distributed fairly evenly around the galaxy, like our own Milky Way, there's a concentration of stars in a particular location in space. So that is a cluster. Okay. So the sort of number density of stars in that volume is higher than it would be typically in the galaxy. Well, why are they there? Why do we get clusters? Well, they're all really linked with how they kind of formed in the first place. Now we're going to talk a bit more about how stars form in future modules, in future lectures in this module. But at this stage, all we need to worry about is the fact that stars will form out of clouds of gas. So there are clouds of gas out there between the stars, and we'll look at those in future lectures as well. And gravity gets going and everything collapses down and the cloud will collapse. And the end result of that is often, well, usually, the formation of many stars, not just one. So you'll get maybe thousands of stars all forming out of one great big cloud of gas that's collapsing and fragmenting under gravity. So that means that all of those stars in that cluster that result from that will have formed at the same time. And they'll have formed out of the same material. Okay, so that cloud, whatever it's made of, all of the stars will start off made out of the same stuff and all start burning their hydrogen at the same time. So in terms of stellar evolution, if you like, their clock starts ticking all at the same time. So we'll see that as we go through this lecture. So that's very important. So let's have another picture of one. There's another rather beautiful picture of a star cluster. So here you can see a cluster of stars here. Okay, so you can see that it's more concentrated here. There are a lot more stars here than there are, say, over here in the general sort of background field of the galaxy. So there's clearly a concentration of stars in the middle of this picture. Okay, you can see a lot of them are bright. You can also see in the red light here sort of some leftover gas, if you like. So there's still some gas hanging around here. We'll talk a lot more about this in future lectures. But this is basically the leftover bits of the cloud that this cluster formed out of. So this cluster has formed recently in this example. But some clusters last for a long time, as we shall see. Okay, so the main focus here is again basically coming back to our Hertzsprung-Russell diagram. Okay. But now instead looking at a different type of diagram, which basically does the same job for a star cluster. So these are referred to as color magnitude diagrams. So remember, our Hertzsprung-Russell diagram is a plot, if it's like an observer's version, then it would be a plot of absolute magnitude. So that's capital MV here, absolute visual magnitude, against spectral type or some measure of the temperature of the star. So for a color magnitude diagram, instead of plotting the absolute magnitude, okay, we actually just plot the apparent magnitude. So little mv, or as we introduced last time, you might often see that written as capital V, even though it's still the apparent magnitude, so don't get confused with capital M sub V here. Okay. And the reason we can do this, and it works for a cluster of stars, it doesn't work for a general distribution of stars, is because the stars in a cluster are effectively all at the same distance. Okay? And so this is the relationship that you've had in previous lectures. So the relationship between apparent magnitude and absolute magnitude. So that basically just depends on the distance to the cluster. So if all the stars are in this spatially concentrated collection of stars and they're all at the same distance, then this is going to be the same for all of them. So the apparent magnitude will be a good measure of the absolute magnitude in this case, and it will just be different by this offset, which you might see in the textbooks. It's called the distance modulus, but not going to worry about that. So that means we can plot apparent magnitude on our y-axis here, and on our x-axis, instead of plotting the spectral type of the star, we can just plot the color. Okay, and so we're going to use the example of the B minus V, so the B magnitude minus the V magnitude. Again, both of those would just be the apparent magnitudes. Okay. So because we've already learnt in previous lectures that that's a very good measure of the effective temperature of a star as well. Okay. So all we're doing here effectively is plotting V for the apparent magnitude against B minus V for the color. And that, as you will see, will give us basically the same information as plotting a Hertzsprung-Russell diagram. And it just, so straight away we will see the pattern of stars that illustrate the evolutionary stages of the stars in that cluster. And you can see that straight away, so without actually having to know the distance even, and without having to go through the difficulties of, getting spectra for every single star and determining their spectral type, or any of that kind of stuff. So literally, you just take a picture of your star cluster in the blue filter, a picture in the V filter, calibrate everything so you can measure the fluxes and magnitudes correctly, and you can plot your diagram straight away. So it's a good shortcut to getting a quick HR diagram without any of the bother. So the bottom line here is that color magnitude diagrams for a cluster of stars, so again, this will only work for a cluster, are basically very similar to a HR diagram for like a whole population of stars. Okay. Now, I said in here that we're assuming that all stars are at the same distance in a cluster. Okay, so that's your first little bit of work for today, is to see how good an approximation that is. Okay, so I'm just giving you typical parameters here for a sort of typical cluster of stars that you might find in our Milky Way. So imagine you've got a roughly spherical cluster of stars that's all held together by gravity, perhaps. Obviously, some stars on the near side of that will be slightly nearer to us, and some stars will be on the far side of that cluster, slightly further away from us. So just do a little simple calculation. So if the star cluster has an angular diameter of 1 degree, okay, so be careful with the units here, and the average distance of the stars in the cluster is 1,000 parsecs. What's the, can you estimate the difference in distance between stars on the near side and the far side of that cluster as we view it? Okay. So you'll need to apply what we learnt about angular size relating to physical size in the first workshop. Okay, so have a go at that problem and come back after the break.